back. We are going to continue our exploration of this wonderful paper. And now we are in position here to study paravectors. We've covered these space-time split, this cross product, and now we're going to study paravectors. So let's begin. Let's cover a few errata from the last lesson. Early in the last lesson, I did a little foreshadowing, and I wrote down Euler's expression. The expression is cosine phi plus I sine phi when I squared is -1. There is a circumstance where the pseudoscalar is actually equal to 1, in which case it's hyperbolic cosine phi plus I times the hyperbolic sine of phi. I think what I wrote down is for some reason I left off the h in the last lesson. And also around 4450, I wrote down this expression, which is true. This is the correct expression. What I think I wrote down is I think I left a 2 here, right? So those two little errors, I'm sure there are others, and I'll cover them in later errata. And we read from the beginning of 3.62. Using the spacetime split for bivectors, we can now write a general multivector in the following way. So remember the original way of writing a general multivector, right, where we just have the scalar, the vector, the bivector, the trivector, and the pseudoscalar part. So that was one way we learned to do it. And then the second way we learned to do it already is we took the scalar and the pseudoscalar part and married them together. And we took the trivector part out and wrote it as the dual of a vector, because every trivector is dual to some vector. And then we paired those two guys up, and we ended up writing this whole thing as a complex scalar plus a complex vector, which I forget how we notated that, but let's just call it V, plus a bivector, right? So this was another way of writing a general multivector. But now what we are going to do is we are going to write it in this form here. So this form, obviously it breaks it into two parts. The part on the right here is distinguished by being the dual of everything in here. So we can, well, let's just start with this part, right? Clearly alpha is just a scalar, so the alpha part just drops right in. The E is a relative 3 vector. So that's a part of the bivector ends up here. And then you have a vector. So the vector just drops right down. I should draw this, right? The vector part just drops right down to here. Then you have beta I, right? That's this thing here. And that is clearly the pseudoscalar part. So this pseudoscalar part goes right there. But then you have another relative 3 vector, but don't forget about this I, right? So this is actually the other half of the general bivector. It's the dual of some relative 3 vector. So this bivector space now is fully accounted for by the dual to the relative 3 vector part and the relative 3 vector part. So basically we've taken B, what I've written as a bivector, and we've broken it up into a relative 3 vector part plus a dual of a relative 3 vector. So B and E, be very careful here to understand how this works. B and E are both relative 3 vectors, but B picks up this duality. So that's why E plus B, I, right, this general bivector, I'll call it general bivector, say I called it D, right, that always can be decomposed into the relative 3 part and another part that is dual to another relative 3 vector. And then W being a vector, so this is a trivector piece. So the trivector piece lives right here. The bivector piece is split between these two halves, and then the scalar part is on the is on this left part. The pseudoscalar half is on the right part. So basically, it's this and everything dual to it. It's another way of using this duality to split the space in two. But the key part is now we're taking the bivector, and it's not landing in one of these two halves. The bivector is sort of split into these two pieces. So alpha and beta are scalars, v and w are proper four vectors. So understand we're talking about proper four vectors are anything that can be written as a, mu, gamma, mu. That's a proper four vector, right? A proper four vector always looks like that. And E and B are relative three vectors. So these are relative three vectors. We have further partitioned each half of the complex expansion to even part and odd part, right? So a bivector is even, a scalar is even, so this part is even, but this guy, the vector, is an odd part. So they're basically saying that this part is even and this part is odd. This part is even and this part is odd, right? A trivector is odd, but a pseudoscalar and a bivector they are even. And when I say even and odd, I'm referring to the grade, right? This is an even grade, a grade 0, grade 2, grade 1, grade 0. And this is grade 1, but its dual is grade 3. And I guess with a way to think of beta, right? Beta is definitely grade 0, but beta I is grade 4, which is also even. All right? So that's looking good. These partitions have 4 components each and are also dual to each other upon right multiplication by the chosen time-like unit vector gamma 0. So the duality they're referring to is this duality. We talked about it earlier, right? The relative three basis vectors get dually transformed into the spatial regular vector basis, and the scalar basis vector gets transformed directly into the spatial or the time-like basis vector of the four vectors. So there's 4 basis vectors here and 4 basis vectors here, but these have 2 different grades and these all have 1 grades. And this movement from here to these relative 3 vectors and the scalar vector is dual by right multiplication. Right multiplication is what it says here, right? Right multiplication by gamma 0, right? So that's the whole point. So, and likewise, you go from here to here by right multiplication by gamma 0. And that's obvious, right? Gamma 1 times gamma 0 is the definition of sigma 1. And gamma 0 squared is, in fact, 1, right? So this is a pretty obvious duality. But notice what it says is, it says these partitions have 4 components each. So what are they talking about there? Well, this is 1 component, and that's 3, right? And that's the even part. And the odd part has 4 components, right? So the gamma 0 duality that they're talking about is the duality between the even piece and the odd piece, right? It's this duality that is defined very specifically by left multiplication by gamma 0, right? The gamma 0 duality, which will take these guys to this vector and this vector to these guys, right? So this duality is not going from here to here, right? The duality they're talking about now is a duality that goes like this, right? That took me a little while to think about. It's obvious, of course, but see, if you're expecting, right, I'm expecting, I'm going to go do a duality like this, but that's the duality taken care of by I. So you have to kind of rejigger your brain and read very literally what they wrote here. We have partitioned each half, right? The partitioning is each half of the complex expansion, 3.44. They call this a complex expansion because you've got, basically, if you look at it, right, every multivector now looks like a complex expansion. That's a good point, actually. Right? This is actually equal to A plus B I, where A is a multivector and B is a multivector, right? So I've turned every multivector into some kind of complex expansion. So, and that's the partitioning that partitioning is the complex expansion partitioning, I guess is the way they're trying to say that. It's got and each of the partition pieces have even grades and odd grades. And those even grades and odd grades inside these two partitions, they're related by a duality right multiplication by gamma 0. We illustrate this duality in figure 6b, which I just showed you. As an important example, consider the coordinate 4-vector x. So what they want you to see is that x, right? X is the coordinate 4-vector, right? So x has got to be written as a coefficient times gamma 0 plus a coefficient gamma 1, coefficient gamma 2, coefficient gamma 3. So this guy right here, that is x, and x is grade 1. It's a vector. And if you multiply it on the right by gamma 0, then according to our thinking here, right, if that is a vector, right, it's a 4-vector, it's not a trivector, which would be over here. It's a 4-vector, so it represents this v. Well, if I multiply it on the right by gamma 0, I should get something that looks like a scalar plus a relative 3-vector. And it's really obvious to see how that works, right? You just take this gamma 0 and distribute it in, because I'm multiplying on the right. Well, gamma 0 squared is 1, so this is your scalar piece right here. The scalar piece immediately pops out. And then, due to the orthogonality of gamma 0 with all the other basis vectors, you get gamma 1, 0, gamma 2, 0, gamma 3, 0, which of course is sigma 1, sigma 2, and sigma 3. And we write that as a relative 3-vector plus a scalar. So look how beautiful that is. So that's really sweet, actually, because we actually, in the study of special relativity, you always see stuff like this, right? You see stuff like this all the time, but this is like a shorthand notation for terms. So this is great. Well, actually, I guess you don't. Of course, you don't see stuff like this because in special relativity's normal study, you don't add a vector to a scalar. So, but you definitely break apart a 4-vector, right, into a scalar part, which is the time part. And sometimes you write it like this, right? And that's sort of what this is reminding me of, intentionally reminding me of, right? That's the whole design of this thing. So continuing, this object here is the sum of a relative scalar time, and a 3-vector of the relative spatial coordinates. So this is that sum they're talking about. Now, what's interesting and what's important to remember is this literally is, when we think of regular elementary physics, this counts as the position in space. You don't need to worry about being an event in time anymore because all of the time lives now in this other part, this scalar part. This combination of a relative scalar and a relative 3-vector is commonly called a paravector. So they want to call this whole thing, this whole sum, a paravector. It's got a relative 3-vector part and what they're now calling a relative scalar time. Well, I guess what they're saying is, if you have a paravector, this part is called a relative scalar. This we've already defined as a relative vector. I don't think they've introduced the idea of a relative scalar quite yet, except to say that a relative scalar is when you do this, I guess when you do this duality transformation of a vector in the space-time algebra, so X is a vector in the space-time algebra, if you do this duality transformation, what you're left with is what they're going to call a relative scalar and a relative vector. But if you just stared at at any arbitrary scalar in the space-time algebra, unless you know where it came from, I suppose it's hard to identify it as a relative scalar. However, in the space-time algebra, if you ever see anything constructed with a basis sigma 1, sigma 2, and sigma 3, you can be pretty certain that you're dealing with a relative vector. So I'm not quite sure what they mean by relative scalar except that it's the scalar part that's left over after you do a right multiplication upon a vector by gamma 0. So if you take the space-time product of gamma 0 on the right with any vector, you're left with these two parts, right? These two parts. And the scalar part, I guess we're going to call now a relative scalar. That's the word. So if you just saw an arbitrary scalar floating around your space-time algebra, it's probably not a relative scalar unless it's floating around inside a paravector, right? That might be the best way to say it. So this paravector is obviously a scalar and relative vector combination that is derived from the duality of a regular vector in the space-time algebra. But we often write this as a tuple. Yeah, there's the tuple I was talking about. I knew I got this idea from somewhere. So this is how you would write a normal 4-vector when you use the word 4-vector in terms of special relativity, right? Remember, we have that problem of a special relativity 4-vector. If I ever say 4-vector in these lessons, the default meaning is a special relativity 4-vector, right? Things that go under these standard Lorentz transformations with 4x4 matrices. The first part is the time-like part. The last 3 parts are the space-like parts. And this is what a 4-vector looks like. And so what they're saying is we're going to take this multivector, this paravector that we've now defined, which is a multivector, and occasionally we're going to be happy to write it as CTX. Notice, by the way, also we're kind of slipping in and out of this notation with. I sometimes can't help it, but just drag CT to equal 1. So I might easily write this very thing as TX, right? When I do that, clearly I'm in this notation where C equals 1. But this paper obviously does not do that. But, okay, so it's often written as a tuple instead of a sum to indicate that the scalar and 3-vector parts of a 4-vector should be considered part of the same unified whole. This is a weird sentence. Okay. The scalar and 3-vector parts of a 4-vector. So a 4-vector like this, I mean, a 4-vector really is just x0, the x0 part, the x1 part, the x2 part, and the x3 part, right? So those are 3 different pieces of a 4-vector. They all have the same units, by the way, right? That's what this C and CT does for us. And when C equals 1, it becomes irrelevant. So clearly, when you have a 4-vector, the whole point of being a 4-vector is that it is a unified object, right? And there is no truly scalar part of a 4-vector. So when it says the scalar and 3-vector parts of a 4-vector should be considered part of the same unified whole, a real 4-vector, they're all scalar parts, right? Every component of a 4-vector written like this are all scalars. So I think what they're trying to say is that the scalar and 3-vector parts of a paravector should be considered as a unified whole. So I would change this to, I'd say the scalar and 3-vector parts of a paravector, right, should be considered the part of a unified whole. That's right, because if you walked around, if your paravector P was equal to alpha plus, say P scalar part, right? Let's see. So say you had a multivector that was a scalar plus a relative vector. You might later on, you might detach this. You might have some calculation that detaches the alpha from the relative vector, and then you kind of lose track that you're dealing with this paravector, I suppose. So if you write it in this form, right? If you write it in this form, you'll keep them kind of together. You won't let them get separated in some calculation. But saying the scalar and 3-vector parts of a 4-vector should be considered part of the same unified whole. I think what they're getting at is if you have a 4-vector like X and you do its duality transformation, this paraduality, they haven't given this duality a name yet, so I'm going to call it paraduality. If you execute its paraduality, you end up with a scalar part and a relative vector part. And this, I guess the idea is that this is the scalar and relative vector part of that. The problem is when you say it's a part of that, you would think, oh, I can partition this somehow into a scalar and vector part, but you can't, right? Because these are all the same object. There's no scalar in there. So they're all vector terms. So it's a little bit of a confusing language there. So I would change that to 4-vector, to paravector. Because if you're a paravector, by definition, being a paravector means you are the duality transform. You are the paraduality, the paradual of a 4-vector, right? You're the paradual of a 4-vector. Okay, interestingly, the paravector that appears here as the sum of a scalar and 3-vector is closely related to the original use of quaternions by Maxwell to describe the essential unification of the temporal and spatial parts of a 4-vector. We will comment more on the close relation between 3 vectors that appear here and the quaternions in section 3.7. Well, this goes back to the history stuff, right, which we didn't study much. But Maxwell did when he first wrote down some of his equations, or I don't know if it was when he first wrote it down, but eventually he was a big fan of the quaternion school of vector mathematics, which did not prevail. So his earlier writings are pretty opaque. I actually looked at one of his early papers. I think I actually looked this paper up when I read through this paper the first time to say, oh, I'm going to see how Maxwell did this. And I got nowhere. It's not like it was impossible to read, but it just wasn't worth it, right? This is something that's more interesting to historians. But the point they're making here is the same point we discussed earlier or in the last lesson. I can't remember exactly when we're trying to claim that geometric algebra is the ultimate realization of the mathematical foundations or the mathematical paradigm that most effectively captures electrodynamics and other things. And every other attempt is some sort of bootstrapped fractional attempt that has to be tweaked and given special little exceptions to make it work. But why is this closely related to quaternions? Well, what they're kind of saying is that if quaternions, remember, had the structure of a scalar part plus, x0i plus, or x1i, well, I don't know, how would you write it? You would write it as xi plus yj plus zk, something like that, where I, j, and k, we know that I squared equals j squared equals k squared equals -1. So there's 3 different square roots of -1. And we also know that I, j, and k multiplied together equals -1. And from this, you can generate a whole multiplication table of quaternions. So it would be a mistake, however, to think how this is a quaternion of some kind, right? Where sigma 1 gets correlated with I, and sigma 2 gets correlated with j, and sigma 3 gets correlated with k, right? That's a mistake, because right away, if you calculate sigma 1 squared, right? Sigma 1 squared is gamma 1, 0, gamma 1, 0. You make one flip, right? So you get gamma 1, 0, 0, 1 with a minus sign. That goes away. These two square to 1. The last two square to -1, which cancels with this -1, so that equals 1. So sigma 1 squared equals 1, and that's true for all of the others as well. And the trick there is understanding that, gamma 0 squared is 1, but all the other gamma squared is -1, and you'll always need one flip. So these guys clearly don't satisfy this rule, so those aren't going to be our quaternions. Well, since we started discussing this, we might as well finish it. So what are our quaternions, right? So just a reminder, we need to find something in our space-time algebra that, well, we need to find three things in our space-time algebra that satisfy this rule. Each of these three things squared is -1, and they need to multiply together to get to -1. And as a consequence of these two things, we discover that ij, the quaternion product between I and j is k. So the space-time product between our two things in our algebra better satisfy this kind of relationship. So the point is, these are the rules for quaternion. So this is quaternion multiplication, and they're defined by these rules. And every quaternion can be made out of I, j, and k and a scalar. So this forms the basis for quaternions. So we need to find three elements of the space-time algebra that obey these properties with the geometric product as the multiplication mechanism. So we've already seen that sigma 1 and sigma 2 doesn't do it. I actually multiplied them together to show that they all do in fact leave the algebra. So meaning that I would expect sigma 1, sigma 2 to be sigma 3, but it's gamma 2, 1, which is not even a relative 3 vector, right? So clearly these guys are not going to be our quaternions exemplars inside the space-time algebra. And so what are? Well, it turns out these three things are, right? So the dual of sigma 1 with a minus sign, because remember, I inverse is minus I. So the opposite of the dual of sigma 1 is going to be related to I. The opposite of the dual of sigma 2 with yet another minus sign is going to be related to j. So this will be our j. And the opposite of the dual of sigma 3 will be our k, right? So it may seem like, well, this is a bit of an odd thing, but that's just what it is. There's this minus sign here seems to be, according to the paper, necessary because quaternions were originally developed to be left-handed, and this kind of squares them up. But that's really irrelevant to us. All we need to do is find three elements in our space-time algebra that behave the right way. So let's check. Well, the first thing we check is, do they each square to -1? And here I worked out the full example for gamma 2, 3. Which is gamma 2, gamma 3, gamma 2, gamma 3. You pick up a minus sign by flipping these two. So you got that minus sign, and then you end up with gamma 2 squared and gamma 3 squared, both of which are -1, and that's -1. And you'll see that that's exactly the same for gamma 1, 3, which is j, and gamma 2, 1, which is k. So yes, they satisfy this property right here. They satisfy this first property. That's a check. Then I just to get a little practice, why not just multiply all three of them together, gamma 2, 3, gamma 1, 3, gamma 2, 1. And I did a flip here, which picks up a minus sign, gamma 3 squared, gets rid of the minus sign, you're left with gamma 2, gamma 1, gamma 2, gamma 1, which is basically gamma 2, 1 squared, which we know is -1. So they also satisfy this rule, right? And then I actually checked to see if they satisfied these rules, right? And you should check these too if you care. But gamma 2, 3 and gamma 1, 3 is gamma 2, 1, which is I. This is I. This is j. And this is k. And just to be very clear, when I talk about I multiplying by j equaling k, this is quaternion multiplication, but this is space-time product, right? The point is there's an isomorphism between gamma 2, 3, gamma 1, 3, and gamma 2, 1, and the scalar basis vector 1, you got to include that, and the quaternions. And so there's an isomorphism between a subset of the space-time algebra. And it's actually, in this case, it really is a sub-algebra, right? Because if we were to call, let's say we just go ahead and call this I, let's rename these bivectors I, j, and k, right? Then any bivector that's written as a scalar alpha plus xi plus yj plus zk. If I take anything like this and I multiply it by another object of the same construction, I'll end up with yet a third object of the same type, right? Which means I never leave the space spanned by this object, this multivector, or spanned by I, j, k, and 1, right? Remember, you got to add 1 to this, right? So if you take the entire piece of the algebra spanned by these three things, and you use multivector multiplication, you will always stay inside that. It's a literal subalgebra. Like we argued about this cross product before for the relative vectors. That's not technically a subalgebra, as I explained previously, but this one literally is a subalgebra. So that's kind of interesting. And the reason it's a subalgebra is because we're dealing with the geometric product, right? The literal product of the overall algebra. And if it's closed under the geometric product, it's going to be a subalgebra. Okay, so that's our little diversion into the quaternions. I don't think it'll be particularly useful for our work. It's more of a curiosity than anything else, I think. So let's continue reading. We see that right multiplication of a 4-vector by gamma 0 isolates the relative quantities. That's the relative scalar and the relative vector. That's what they're talking about here, the relative quantities. So this affirms what we were saying before, right? Right multiplication by gamma 0, the scalar that results, we're going to call that a relative scalar, so they're introducing the term late, right? Here they drop this notion of relative scalar. They definitely well-defined a relative 3-vector. We got that locked down. But then all of a sudden the word relative scalar appears, and its definition is finally provided in the next paragraph. So that's kind of a tricky flow of thought problem, right? But we got it now. So we isolate the relative quantities that correspond to the inertial frame of gamma 0. So it's very critical to understand, the inertial frame of gamma 0. What does that mean? Remember, that's the way the language is going to go from now on. So we got to be real solid with that. But what we're basically saying is you're setting up a reference frame in space-time, and gamma 0 is the time-like basis vector. It's a purely time-like basis vector. And this reference frame belongs to whatever observer is just moving along with a 4 velocity that's entirely gamma 0. So the 4 velocity of the observer is, it's going to be CT0. It's going to be CT0. That's the observer. That's the guy who owns that reference frame in the sense. They're motionless in their own reference frame. And gamma 0 represents the movement of that origin of that reference frame. And so it's their 4 velocity too, right? That's the other important point. Because remember, the 4 velocity squared is always equal to c, which in most systems that are done intelligently equals 1, right? And so because of this, the 4 velocity of anything is eligible. I should get rid of that square. The 4 velocity of anything is eligible to be the gamma 0 of a reference frame, right? That's the important thing to remember there. So they say it corresponds to the inertial frame of gamma 0. So that language is what I'm worried about confusing people. The inertial frame of gamma 0. That means the inertial frame of an observer who's stationary in that inertial frame, whose 4 velocity is gamma 0. So basically, gamma 0 is the 4 velocity of the observer most comfortable in that inertial frame. I mean, because inertial frames can have 4 velocities that are not purely that they're always going to be time-like, but they're not purely going gamma zero, right? You know, anybody that's moving uniformly defines an inertial frame, but it's this particular inertial frame is where you're stationary in that frame, and that's what they mean by the inertial frame of gamma zero. Left multiplication flips the sign of the three vector part due to the wedge product in the three bases. So here they do an example. So they mean left multiplication by gamma zero, right? So here's the opposite effect, right? And of course you come in with a negative sign on your, because now you end up, in order to get sigma 1, you end up with a gamma 0 wedge gamma 1, which equals minus sigma 1. So that's where that minus signs are going to come from. So left multiplication gives you this. Thus, we can consistently recover the invariant coordinate interval in a direct way by using paravector duality. So they say, okay, x squared, that is going to be, if x is a position vector in space-time, right, which is way we write down an event, right, we write down an event, t x, right, we write down an event. That's one little instant in an event in space-time. So normally we would say, okay, this interval, right, we all know is t squared minus the magnitude of x squared, right? That's the square, well, that's the square of the space-time interval, right? That's s squared. That's from special relativity. So what they want to say is, well, x squared, that what is x squared going to be? It's the magnitude of this event's position vector. Well, they throw in this pair of gammas, they find the space-time split of the one on the left, and they find the sort of anti-space-time split of the one on the right, which gives us this expression and this expression, which clearly multiplies out to the scalar ct squared and then x squared, right? And then they say, oh, well, look at that. That's a legendary formula. So that's pretty easy. And that is kind of convenient. I do think they kind of overstate the next part, though. I'm not sure. I'm not so good with this stuff yet that I can say they overstate it. But observe that this style of derivation has completely bypassed the need to expand the expression in explicit components to obtain the final result. This is a general and convenient property of working in the space-time algebra. Transitioning between proper and relative expressions is a component-free and straightforward exercise. Well, okay, so what I'm trying to understand is exactly what is the alternative view here. So I guess what they're saying is, if I were to do this in the old way, I would have said, okay, here's my space-time position vector. It's x mu, gamma mu. And I want to calculate this object, which is this metric, and then I would have blown it up like this to get my answer. And that is compared to this exercise here. Sure, this definitely is a little bit tighter, right? You do have to remember this clever move of inserting gamma 0, and it's not like components don't exist at all, right? Because you do have to choose this gamma 0 in there. But fair enough. You do derive this, although remember to calculate these things. I mean, t is a component, right? And to calculate this, you are going to ultimately need the components to get the number. So to get a number out of this is going to be a problem. But to get this sort of symbolic connection between something that doesn't depend on vector coordinates at all, symbols that don't have any components at all, just throwing in these gamma zeros and understanding this notion of the relative space-time split does get you here pretty fast, as long as you don't actually want to calculate a number, where eventually you will have to decide what these components are, as far as I can tell. Anyway, so that's good. So using the vector-paravector duality, we can further expand the multivector 3.44 into a fully frame-dependent form relative to gamma 0. Okay, so let's look at this thing. Okay, continuing on. Using the vector-paravector duality, we can further expand the multivector 3.44. Now remember, 3.44 was this guy, right? So we're going to further adjust this guy again. Now remember, this guy has a paravector here, right, which is a scalar and a relative 3 vectors. So this is a paravector. And this is a proper vector. I can't write PV for that, so I'll write proper vector. And likewise, this piece has, again, a paravector and a proper vector, right? And we know that those two are related to each other by right multiplication by gamma 0, and that goes both ways, right? So right multiplication by gamma 0, right multiplication by gamma 0, in a sense, right? There's a duality in there. That's sort of the gamma 0 duality, I guess the relative duality. So, we're now going to make some change to this organization. It's still the same multivector, and it's still the same total basis for the geometric algebra. We're just shuffling things around in more useful or telling ways. So what is our next telling way? Well, the next telling way is we're going to shift it into a fully frame-dependent form relative to gamma 0. Fully frame-dependent form relative to gamma 0. Well, we already know that this paravector part is dependent on gamma 0. But what wasn't dependent on gamma 0 before was this used to be v. That used to be a proper vector. Now what we're doing was just saying, oh, to heck with that. We want to find we're going to take that proper vector, drive it through the relative duality, and get a paravector out of it, right? So that paravector, then we're going to push back into this with yet another sort of gamma 0 dual change. And so we're going to redefine this. This is actually v, right? Right? In other words, if we take v, we take gamma 0, we're going to get delta plus p, right? And then if we take gamma 0, then if we take delta plus p, right, and we multiply by gamma 0, we're going to get v, right, which will be delta gamma 0 plus p gamma 0, which is going to end up being p1 gamma 1 plus p2 gamma 2 plus p3 gamma 3, right? So we're rewriting everything in terms of paravectors. We're squeezing as many paravectors in as we can. So this is just a free-floating paravector. This guy in its totality is a proper vector, right? But we're expressing that proper vector in terms of a paravector as the dual of a paravector. I guess that's the best way to say it. We're taking what was in the previous formulation just the vector v, likewise over here, this was the vector w, and we're now writing it as a paravector, as the dual of a paravector, all right? So that's the way I see this. And this is into a fully frame-dependent form relative to gamma 0. Everything depends on gamma 0. Gamma 0 not only is dependent here, but it's also buried in here too, because remember, the split between E and B, this split heavily depends on gamma 0, right? Gamma 0 is what defines sigma 1, sigma 2, and sigma 3. You got to get that gamma 0 right. And we're just saying there's no quantity in this entire expression that doesn't depend on gamma 0. Because this is a paravector, so alpha and E depend on gamma 0, likewise here, likewise here, likewise here, and that's everything. That's everything. And even I depends on gamma 0, right? Because there's a gamma 0 in I. So that's the point of this. It's now completely frame dependent. So it involves only paravectors, and here are the scalar parts and vector parts, the relative 3 vector parts, and the appropriate duality factors, gamma 0 and I. So we've fully exploited these two dualities to write an arbitrary multivector in this frame-dependent form. These paravectors are quantities usually considered in frame-dependent treatments of relativistic systems that use traditional vector analysis. Right, so you can see that they're kind of leading us on, right? You've got electric fields, magnetic fields, momentum vectors, right? And so with that, when you use normal basic special relativity, you use all those things to do your calculations. However, the geometric origins of these quantities becomes obscured when they are lifted outside the space-time algebra. And that's true, right? We don't think of momentum as a geometric three momentum as a geometric quantity, right? But inside the geometric algebra, we say, oh, that's a bivector, right? We know it. This looks like a little vector in here, but remember, it's a bivector, right? E is a bivector. This is the time-like part of a paravector, which means it's the time-like part of a four-vector. Things like that. So that's true. It's just we have to decide eventually how much is this geometric origins of use to us. And I'm sure that the more you do this, the more useful it becomes. And until you use it a lot, you can't just articulate the usage. You've got to actually live it. So we can recover some distinguishing information about the scalars by examining their behavior under frame transformations and spatial reflections. Actually, I think we'll do that next time because it does involve a pretty detailed study of this table here. And what they want to show you is all of these things that we learned about in regular physics. Axial three vectors, polar three vectors, pseudoscalars. Well, we didn't learn about pseudoscalars very much in regular physics. There were no pseudoscalar objects. Magnetic monopoles would be pseudoscalars, right? There's some pseudoscalar particles in physics, right? So that's important. But relative scalars and proper scalars, we're going to show how all of those change under parity, and I think that's the distinguishing feature. This is not quite as important, but the point is geometric algebra, this stuff is very clearly living in geometric algebra in a logical way. All of these properties of being polar or axial or pseudoscalar, you don't have to worry about them. You don't have to remember any of that stuff. It just sort of happens because of it's all accounted for in the bookkeeping of geometric algebra. And all of those behaviors are demonstrable in terms of geometric quantities. It's all logical from things like the fact that A wedge B is minus B wedge A, and that becomes geometric when you think of it in terms of, oh, we're talking about an oriented piece of area in a plane. All of that accounts for this axial and polar business, right? Okay, so I don't know. We probably won't dwell on that too much next time, but hopefully we'll get through this section on paravectors next time. Let's see, where do we need to go? And we'll cover relative reversion. All right, so we'll see you next time.